Okay, can we start now? Are you ready?
Yeah, sure.
Okay, so it's my great pleasure to introduce Yunju Kim from Columbia University, and he's going to talk about singular fibers of some minimal abelian vibrations.
All right. Thank you very much for the invitation to the NCTS AG seminar. Yeah, I can't really see how many how many people there are through the camera, but yeah, I'll try to like answer all the questions. If there's any question, I don't know how it works. Like, please stop me in the middle and then yeah, ask the questions. So first of all, disclaimer. So I really should have mentioned Matsushita and Juan Guiso's work during the talk, but somehow I wasn't able to, state their result in between the, some bunch of like things to sort of like not stop the flow. So I'll just mention it at the beginning. So this work is highly motivated by 2001 paper Matsushita and a series of paper by Huang and Guiso. Okay. Everything is going to be able to see. So the paper is out on archive just a few days ago. I think it's like 2 days ago or so. So you can check everything on archive if you're interested. So everything on archive, the paper is written in the algebraic category actually, because I'm not, technically very strong in the analytic category. But anyway, so for the simplicity of the exposition, we're going to use analytic category here. So S is throughout going to be a one-dimensional open disk, and then if I want, I'm just gonna shrink it. So epsilon can be arbitrarily small, epsilon the radius, and this is a zero basically. So I really wanted to write it zero, but my notation is going to be S0 being the complement of the zero of the open disk. So this is the puncture disk. So I didn't use the zero for the reference point. Sorry if it is confusing. Okay, that's a notation. All right, so let's begin with elliptic fibrations over unit disk or the epsilon disk. Um, so elliptic fibration for us is a flat projective morphism. Um, this is going to be the notation throughout f from x to x, such that over the puncture disk, over the puncture S0, the pre-image of this flat projective morphism is going to be smooth. Okay, what that means is that outside of zero, outside of the S, okay, I'm just going to call it S. Little s, which is a reference point, it's going to be just a family of elliptic curves, smooth projective family. But at the point zero, yeah, it's going to be something wild can happen, right? So that's a elliptic fibration for us. So the elliptic fibration is called minimal if the following two conditions are satisfied. If it is minimal, first of all, the total space of this elliptic fibration is smooth over C. And second, this is minimal in the sense that you cannot contract any -1 curve to make the minimal elliptic fibration smaller. Okay, so the fiber central fiber cannot contain any -1 curve, meaning it's a P1 whose focal self intersection. You can define the self intersection because the proper map is a -1 curve, is -1. Okay, so here's a simple example, which is super explicit. If I want to consider the following variety X containing P2 across the unit disk, where lambda is a coordinate of S, the disk S, and I didn't homogenize this, so this really should have y squared z equals, everyone knows. So that's my family. Then you can see that when lambda is not equal to zero, when lambda is not equal to S, which is my notation, the central fiber, then this is going to have three different roots. So that's going to be an elliptic curve. Okay, so that over the S0, it's going to be an elliptic curve. But over the central fiber, x little s, when lambda is equal to zero, you get this guy, and then the singular fiber will look like this, which is precisely a nodal elliptic curve, nodal rational curve. Okay, so the singular fiber may not be an elliptic curve, and then yeah, it can be even rational. So of course, this minimal elliptic fibration this notion is very standard, and then people have been studying a lot since I don't know, maybe even before Kodaira, but Kodaira in the 1960s, successfully classified all possible singular fibers that can arise as a central fiber excess in the minimal elliptic fibration, which was a very nice result in my opinion. So let me review that. So this is Kodaira's theorem, Kodaira classification theorem. There were like so many paper about this written by Kodaira. I don't know. I feel like there are at least 6, 7 papers, Kodaira's paper, one in Annals, one in JAMS, and so on and so on. There's so many papers. But anyway, so the upshot is that he classified all the central fiber, the singular central fiber, and he listed them all. So here's the list. So the first case is called a semi-stable fiber. So the semi-stable fibers are usually written as 1R, where R is at least 0. So when R is equal to 0, that means there's no singular fiber. The central fiber is really an elliptic curve, meaning your vibration, minimal elliptic vibration is a smooth projective morphism. The second case is the simplest case in some sense, is the nodal rational curve. We have just seen it in the previous example. So that's like this guy. Okay, so I would like to interpret in this talk, this guy is P1. I don't think I can write outside of this. Sorry, but I need to write somehow inside of this. This guy is this guy with this point and that point identified. Okay, 0. Let's say this is 0 and this is infinity. And I want to consider the nodal rational curve like that. And then the 1R type for R greater or equal to 2 is a cycle of R number of P1s. As you can see, for example, here's the 1, 5 and the 1, 2 type, where they have 2 special points, 0 and infinity, and then they're successfully identified. For example, this guy has the 0 and infinity. Let's say this is 0, 1 and infinity 1 for the first component. This guy has its own 0, 2 and infinity 2, and then you can see the 0, 2, and the infinity 1 are identified. And then you do it cyclically so that it becomes a cycle of R number of P1s. Okay, that's what it is. That's possible semi-stable fibers. And Kodaira classified what's called unstable fibers. So unstable fibers are basically not semi-stable fibers. And he classified them all and then named it as type 2, 3, 4, 2 star, 3 star, 4 star. And then there's another series of example, 1R star, where R is at least 0. So type 2 is what's it called? Is a cuspidal rational curve, as you can see. Type 3 is a tag mode, like this. This is basically y squared equals x to the 4. And then type 4 is actually is not very hard to draw. Type 4 is a union of three lines, which is given by x, y, x plus y equals 0 in P2. That's what it is. And then like you have a whole zoo of possible unstable singular fiber. This is 1, 0 upper star fiber. So star indicates that your singular fiber may be non-reduced. So here you can see that this 1, 0 star fiber consists of 5 rational curves, smooth rational curves. But this middle rational curve has multiplicity 2. So this is a non-reduced fiber. Similarly, 1, 1 star type has 2 P1s with multiplicity 2s, and all the other 4 P1s, they have multiplicity 1. Anyway, so this is a possible singular fiber, and so on and so on. This is a 2-star type, which is very complicated. 3-star type, you even have the 4-star type. Let me not draw the 4-star type. Okay, so those are the semi-stable fibers and unstable fibers. So usually when people say it's unstable, it really means that it's not semi-stable, meaning that the unstable fiber contains a multiple fiber. But throughout this talk, my unstable fiber is not is a non-multiple unstable fiber. Okay, so I want to distinguish the multiple fiber and the non-multiple fiber. So let me state in this way. So the multiple fiber, which is not unstable, it should be always in the form n times its reduction, where x as red is a type 1R fiber above, the semi-stable fiber above. So it's like a cycle of P1s. Okay. But then every P1 has multiplicity n. So that's going to be a multiple fiber. Right? So in some sense, this multiple fiber behaves as if it is a semi-stable fiber. Okay? This is behaving semi-stable? Semi-stable? As if it is. It is. Okay, so that's a side note, which is going to appear again later. So the goal of this talk, the goal of today's talk is to partially generalize this Rosado-Kodaira about the singular fibers arising in minimal elliptic vibration to higher dimensional singular fibers arising in the degeneration of higher dimensional B-line varieties. And that's the goal. But to do so, I would like to focus a little more on the case of elliptic curves because elliptic vibrations, because basically it almost contains all the what's it called? All the phenomena, not all of them, but though. But it still is, a family one-dimensional thing, so it's like easier to draw. So let me just stick to the elliptic vibration a little more, and then move on to the higher dimensional case. So, all right, questions so far? I really have no idea how many, and okay, all right. The next section, the next thing I want to talk about is the comparison of minimal models and what's called the narrow model. All right. So still we're in the world of minimal elliptic vibration. So minimal elliptic vibration is a minimal model. Of course, as the name indicates, it's a relative minimal model over the unit disk. S. So in the case of surfaces, in the case of relative dimension one over a one-dimensional base, the minimal model is always unique. Is it always unique? Um, okay, let me say at least in this case, it's unique. Okay, so it's unique in its birational models, meaning that if you have another, let's say, x prime, okay, and then it's birational to each other, then this is minimal. And then, yeah, so if you consider all these x primes, then there's this specific choice of minimal model. And then if there are two minimal models, they're isomorphic. Yeah, you know what it is. All right, so that's what it is. And then the good thing about this minimal model is that you don't actually need a central fiber. So if you start with a complement of the central fiber, which is an honest, smooth projective family of elliptic curves, then there's just a unique minimal model. So whatever the central fiber is, yeah, so you don't even need to think about the central fiber. You just like there's a formal way of extending it in some way. That's a good thing about the minimal model, right? Okay, so we're gonna think about more models, not the minimal models, and then that more model is called the narrow model. But let me give you an example of a model. So there's the notion of a Weierstrass model, or sometimes people call it a minimal Weierstrass model. I guess that's the more standard terminology. Anyway, a minimal Weierstrass model is among all these birational classes. It's a morphism, flat projective morphism y to s from y to s, such that the total space can have canonical singularities. You don't assume it's smooth, but you assume that the central fiber is necessarily integral. Okay, so it turns out there's a unique minimal such thing by minimal Weierstrass model among all the birational models of that. So that's one possibility. That's one possible model that we can consider. Yeah. Yet another possibility is called a narrow model, which is, I believe, less well known I don't know, to some people. I guess I got the impression that this is more popular in number theory people. I don't know. But yeah, definitely some people know. So anyway, so there's this notion of a narrow model that we're going to introduce. So the characteristic property of the narrow model, this P over S, it's not going to be proper over S. It's not a proper model S, but by sacrificing the properness, it's going to be even smooth, not just flat, but smooth and quasi-projective. And it has a group structure. It will have a group structure. That's the reason why we're interested in the narrow model. So let's define the narrow model. So this is actually a real hardcore theorem, Néron, but let me consider it as a definition. So we start with a smooth projective vibrations whose fibers are all genuine elliptic curves, so it's smooth projective. And let's assume it has a section. Okay, and the role of the section the role of this section is that you can consider this guy as an abelian scheme, so it admits a group structure. So I really wanted to write it here. So it's like if I have a punctured, this is a puncture, this is S0, and then this is P0, and yeah, so this is punctured, I don't know what it is, and then I'm given a section. Okay, so this is a situation, and then in this case, every fiber by fiber, it admits a group structure because it's an elliptic curve with a preferred zero, right? And then what I'm gonna do is that I'm gonna be a little fancier, and then I'm gonna consider the sheaf of all analytic sections of this guy. So what that means is that for every I can't write it on the black part, so I'm gonna have to, for every analytic open neighborhood U as 0, I'm gonna set P uh, P0 sheaf U0, the U to be the set of morphisms from U to P0, PU. Okay, so it's a P0 as 0, and then U, and then I'm gonna consider all the sections, analytic sections. There's a little bit of subtlety about the essential singularity, but let's just completely ignore this. Anyway, so that's a sheaf. That's a sheaf of abelian groups because P0 was an abelian, commutative group scheme. So it's a sheaf of abelian groups. So why don't we take a push forward, a stupid push forward by the open immersion S0 to S? That's like I don't know what it is, but at least it's an abelian sheaf. And Néron's theorem is that this is actually representable by a smooth, quasi-projective, and commutative group scheme. So it's representable by an algebraic object. So that's P over S, that's the Néron model. And if you think about it, there's just like a priori no reason at all why this should be representable. And I believe it's a highly non-trivial theorem. Yeah, although, yeah. So describing the central fiber over S is a different story because yeah, we're gonna do it soon, but at least it's well defined, some smooth commutative group scheme. Good. So what are we doing? So we had a perfectly well-behaved minimal elliptic vibration, which we're interested in. That's the main interest. Sorry. So before that, let's start with the family elliptic curves with a section. Okay, this is either x0 over s0, which is part of our minimum elliptic vibration, but at the same time, because I want to emphasize this is a group scheme, I want to also write this as P0. When I write down the letter P, it's a group. When I write down the letter X, it's a minimal focal minimal elliptic vibration, abelian vibration. Anyway, so there are two unique models that we can think of. Either use the NMP to construct the minimal elliptic vibration, filling in the central fiber by some XS, and then we can construct, similar formally, a unique Néron model by filling in the central fiber by some group object, smooth group object, commutative group object. Okay, so the question is that what is the relation between these two objects? And that's again a very hard question, but Néron successfully answered that in the case of elliptic vibrations. So in this situation, it turns out miraculously, or I don't know, it's very surprisingly, P is the complement of X by the singular locus of the central fiber. Okay, so P has to be smooth over S, so this singular locus of XS cannot be contained in P possibly, but then if you just remove it, that's going to be all of P. So moreover, what's even more surprising is that because P is a commutative group scheme, you have this group structure, which is a holomorphic map / a morphism. This morphism actually extends to this group action morphism. Because P is an open subset, open Zariski open subset of X, so I'm claiming that this guy is a Zariski, it extends to that morphism. Unique extends. Okay, that's a rather surprising theorem. So what is it? So what's going on? So let's think about an example. So let's think about our previous example where your minimal elliptic fiber has type 1,1 fiber, meaning that the central fiber is a nodal rational curve, the simplest case. Okay, so that's the picture of the previous picture of the minimal elliptic vibration. And then I can also, so let's assume there's a section so that I can also consider the formal Néron model as well. Okay, so a priori, the central fiber of the Néron model is unclear, although we do know that the central fiber has to be an algebraic group or a Lie group. Okay, so general fiber of P and general fiber of X outside of the reference point is all elliptic curve by definition. Good. Central fiber of X, we have assumed that this is a nodal rational curve. That's the assumption. So what is the central fiber of PS? According to the theorem of Néron, it's the complement of the singular locus of the central fiber. Okay, so the central fiber of this guy is just the complement of this node point. Okay, it's a nodal rational curve minus the node, which becomes a quasi-projective smoothing. And you can convince yourself this is actually A1 minus 1. This is P1 minus 2 points. So that's A1 minus 1 or C star. Or if you want, this is GN, C star. Okay, that's an algebraic group. So, and Néron's theorem is that this is actually the Néron model varying smoothly along the family. Okay, so the second, yeah, actually there's a second content of the theorem before Neron's theorem. So Neron also claimed that this guy acts on the entire X. Okay, so in this case, a rather silly situation. So that means the central fiber PS, which is GMC star, acts on the entire nodal rational curve. So what's the action? So outside of this node, it's, outside of the node is the same as C star, and C star acts on C star by multiplication by itself. Okay, that's how it acts. At the point this node, the C star action is trivial. Okay, so in this case, it's rather a little silly, but yeah, in the non-1-1 fiber case, it's going to be more complicated with that. Question? Okay, am I going too fast?
Sorry,
Yes.
sorry. In your last page,
Yes.
the uniqueness is up to birational. Uh,
Uniqueness of which object are you talking about?
in the middle, NMP constructs a unique.
Yes. No, it's unique up to isomorphism.
Oh,
So
okay.
whenever, yeah, whenever the two minimal elliptic fibrations are birational to each other, then it's necessarily isomorphic.
Oh.
Does that make sense? Okay, yeah. Yeah, all right. Thank you for the question. Yeah, similar Neron model is also unique up to isomorphism. It's a canonical object. Okay, so what do we do? What we have done is that I'm just gonna think about it. I mean, so sorry about this, but I am not going to present any kind of a proof whatsoever in this talk. But I'm just gonna think about the way I want to think about these. Yeah, we want to think about these things. So start with the over the punctured disk. Start with the genuine. Oh wait. Why is this happening? Smooth projective family of elliptic curves, okay, with a section so that it becomes a abelian scheme of relative dimension 1. There are two natural ways of extending it to some models over the entire S. So one is a narrow model, the other one is a minimal model. Okay, so in other words, there's a bijective correspondence between the narrow models and the minimal models together with a section. If the minimal model has a section, then there's a narrow model by sending it to, this Neron's theorem, P equals X minus the singular locus of the center fiber. The inverse correspondence is that you send the Neron model P and then you run the NMP. You don't even need the center fiber to run the MMP. Just like consider an arbitrary compactification and then run the MMP. That's going to give you a unique minimal elliptic vibration, which is your X. Okay, that's a bijective correspondence. So both of them have their own strength. I mean, both of them has their own, what's it called? Pros and cons. So the first one, the Neron model, is good in the sense that it is a commutative group. It's a family of groups, so you can literally add and subtract the sections, subtract the elements, which is a very strong constraint, very nice property. And the second one, because it's a flat projective morphism, you can do geometry a little better because, whenever you want to like intersect the two, there's no intersection theory going on here, but like there is. Yeah, anyway, so like Bezu's theorem kind of thing, the intersection is more well behaved in the project proper setting. Okay. So actually, it turns out, exactly because of this reason, classifying the central fiber of the minimal elliptic vibration and classifying the central fiber of the Neron model are intimately related. So if you want to classify the central fiber of XS, you can do it without the Neron model, but if you know what the Neron model is, then you can do it easily, and vice versa. If you want to classify the central fiber of the Neron model, then you don't technically need the minimal model, but if you know the minimal model, it's automatic, I guess. It's because of this reason. Okay. So they somehow like have a little bit of different information. One has the group structure and the other one has the geometry structure. Okay. So using this, actually Kodara also in his paper, of course, without using the word Neron model, classify the central fiber of this Neron model, which is the group. So when XS is semi-stable, in other words, as type 1, then the central fiber of the Neron model turns out to be ZR times GM. This is the reason is, I mean, this is not a proof, but let's say you have a 1,5 fiber. This is one fiber. I drew it before. It's a cycle of P1s. So what is the singular locus of this fiber? The singular locus of these fibers are, of course, 5 intersection points, the nodes. So if you pull them out, then each of the component, for example, this guy is P1 minus 2 points, that's GM. Okay, similarly, the second one, this is GM, 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 GM. And then I'm telling you this is a cycle literally Z5 times GM. So that's what's going on. When excess is unstable, then we do have all the pictorial description of the unstable fibers. So PS can be sort of decided, except that, okay, so PS, the answer is that PS is a product of two groups where the GA is just C, and then this is a finite group, which is called a component group. And this component group should be either trivial, Z2, Z3, Z4, or Z2 squared. Okay, so a finite abelian group of order 1, 2, 3 are necessarily cyclic, so that's good. But a finite abelian group of order 4 can be either Z4 or Z2 squared. So there's a little bit of ambiguity that you cannot deduce from the picture, because if you draw the picture and then count how many components this PS has, if it is 4, you cannot deduce. You cannot check whether it is this guy or that guy, but except for that, it's almost decided. Okay, so let me not cover this example because we have covered many of the examples before. So yeah, so this is the Kodaira type 1 4-star case. So this is the minimum elliptic vibration where the fibers look like this. P is the complement of the singular locus of the singular fiber. So it's a complement of these 4 union of 4 non-reduced parts. So the only parts remaining in this is this part, except for the intersection. So these are all GA, GA, GA. So that's 3 GAs. So that's Z3 times G. Okay. So, and the nice exercise is to check how this acts on how this PS acts on the entire singular fiber axis. Let me just get it. So the upshot is that, as I said, the classification of the non-multiple, i.e. Minimal elliptic vibration together with a section, is more or less the classification of the central fiber of the Néron model. So, although it is not exactly equivalent, but there's a way to go back and forth. Okay, so the reason why I'm talking about this is because for the higher dimensional case, if you want to generalize the Kodaira classification, I do not know how to do it without classifying both of them together. So I need to do partially classify this part, and then using the information of this, I need to get a little more information on this guy, and using this, I need to get a little more information on this, and then complete this to get the complete classification of both of them. So it's going to be like a back and forth.
Excuse me. So, could you remind the importance of the assumption of existence of section in this context?
So throughout this section, I basically assume, right, so this Néron model business in this section number 2,
Yeah.
I basically assume all the time that the minimal elliptic vibration has a section, which is equivalent to saying that the central fiber has at least one reduced component, because I can shrink my, S, whatever I want. So there's a local section passing through the reduced component. So yeah, so in that situation, you have a complete parallel theory of Néron model theory and the minimal model theory. But that's the next remark. The next final remark is that, well, okay, if there's a complete parallel, whatever, between dictionary between the Néron model and the minimal model, when the minimal model has at least one reduced component as a section, how do you consider how do you interpret the multiple fiber? Okay, in other words, when the minimal elliptic vibration has no section whatsoever, even if you shrink your epsilon disk, or epsilon's super small. So in this case, this guy, the complement of the central fiber, is no longer an abelian scheme because there's no section. You cannot add them. There's no reference 0 section. But it's going to be a torsor under some unique abelian scheme. So I'm not going to explain how to construct this unique abelian scheme. So there's a lot of construction going on in this discussion. I'm not going to explain anything about the construction part. Anyway, but the point is that even if it doesn't have a section, there's just a unique way of obtaining an abelian scheme. So this is the diagram that I'm explaining. So if you have minimal elliptic fibration, with or without a section, let's assume it doesn't have any section because the central fiber is multiple, then you restrict it simply to the puncture disk. That's a torsor under a unique abelian scheme. There's a unique way of going this way. And of course, this guy is a torsor direction. And then because now that you have an abelian scheme, which does have a section by definition, so you can apply the narrow model theory here to get the narrow model still. Okay? So even if you don't have a section of F, the minimal elliptic fibration, there's one more step to think about, and you can get the narrow model. That's good. And then as you can expect, this narrow model does act on the minimal elliptic fibration. Again, that's a non-trivial theorem. But it is not true that P is the complement of a singular locus of the singular fiber of X. That is not true. Yeah, that part is false in this situation. So the multiple fibration can be interpreted as a minimal model of a twist of this abelian scheme. Okay, and that sort of like gives you a feeling how you can treat the multiple fibers. So there's always, even if it doesn't have any section, with or without a section, there's always a group object, the narrow model P, and there's restriction P0, which is an abelian scheme, and then it always plays a role. So you need to consider them both. Computation of the central fiber in this situation, this doesn't compute any central fiber. It's just like a way of thinking about, yeah, this situation. Okay. So that's a little annoying situation, but yeah, if you want, you can always assume there's a section because multiple fiber is, in my opinion, multiple fiber is like 3 times harder than the non-multiple fiber situation. Okay, so let's generalize these discussions to the case of higher dimensional abelian fibrations. Before that, are there any questions? Because I'm going a little too fast.
So just so I'm clear, so I mean, what's your assumption on the base? Like, you're not assuming S is a curve or anything like that. Like, I'm just trying to figure out the classical existence of narrow model for say abelian varieties over function field of a curve, for example. So we have the distance theorem, but I sort of don't quite see that structure in your setup.
Sorry, so your question was that when does the narrow model exist? Under what circumstances the narrow model exist? Is that your...
Yeah, for example, or how does the narrow mapping property expressed in your setup? Those kinds of things, if that makes sense.
So the narrow model exists as far as the base is a curve, a smooth curve. So the setup is that you need to consider a smooth
this
curve.
is exactly sort of.
Oh, okay. Did that answer your question?
Kind of. I mean, so when you sort of apply that result to your setup, I mean, sort of what's the sort of issue then? You're sort of wanting to try to understand I mean, if you just sort of apply that theorem off the shelf, sort of how explicit is that in your setup? That makes sense.
Okay, yeah, sure. Yeah. So so actually, yeah, so there's a little bit of subtlety because I believe there's an analytic theory of narrow models. I think I heard about it, but honestly, I don't know much about it. And again, my paper was written in the completely algebraic setup, so it's gonna be like a spec of a DVR or like an arbitrary, like a Dedekind scheme or something like that. So technically speaking, we should have done all the discussion in that setup because the narrow model theory is, I believe, more well behaved in the algebraic setup. But yeah, I just feel like working over the analytic category is easier in the talks. That's what anyway,
Okay,
the point.
Sort of that, yeah. So I haven't looked at your paper, so this sort of that helps to clarify a little bit.
Oh, okay.
Okay, so then as you sort of say, the issue then is higher dimensional bases or something like that, or
Over the higher dimensional bases, narrow model most of the time does not exist. But for example, narrow model of a higher dimensional abelian variety, let's say. But I have another result claiming that if you have a Lagrangian fibration of a hyperkähler manifold, then somehow the narrow model does exist over the higher dimensional base. But there's a little bit of positive result like that. I believe there are many negative results, but anyway, so it doesn't always exist. But over curves, it always exists.
Okay, and then finally, sort of, are there any sort of restrictions on, say, Étal points or hence salient point or
So can you, if there's
So
restrictions on
the
what?
goal, sort of the weak neuron mapping property compared to the sort of absolute, does that sort of come up in any of your setup or?
The weak neural mapping property will be equivalent to the neural mapping property in our setup because we're going to apply the neural model theory only for abelian schemes / abelian varieties. So when you apply neural model theory to group schemes, then the weak neural mapping property does imply the neural mapping property. So yeah, but I'm not going to use any kind of neural mapping property whatsoever in this talk. I'm just going to consider the neural mapping property as a black box in the neural model. It's just, yeah.
Okay, no, good. Okay, so thanks, that helps. Thanks.
Yeah, you're welcome. Thank you. Yes. Right. So basically, I am ignoring all the technical difficulties in this talk. That's what it is. Okay. I'm even like lying a little bit because technically speaking, the neural model theory should have been applied to the algebraic setup. You put the, yeah. Okay. So, but I confess to you, so it's good. So we're going to talk about higher dimensional abelian fibrations now. So as I told you, there's a difference between the two cases. The higher dimensional abelian fibration with a section and without a section. The other one without a section being the torsor issue. You need to like have the torsor issue, but that philosophical understanding doesn't help whatsoever to classify the central fiber in the non-section case. So anyway, so that case should be considered separately. We're going to focus on the first case when there's a section. So what is an abelian fibration? Abelian fibration is simply a degeneration of abelian varieties in the sense that you have a flat projective morphism f from x to s, such that outside of the central fiber, which is S0, s minus little s, is literally a fast smooth projective family of abelian varieties. All the varieties are abelian varieties of dimension n, let's say. And I should emphasize that the polarization type of the abelian varieties plays no role whatsoever in this talk. So it can be applied to arbitrary polarizable abelian varieties. Okay, that's the abelian fibration. So this is going to be minimal if, first of all, the total space have terminal singularities, but actually secretly there's a lemma that in our situation of interest, in our case of interest, it's going to be automatically smooth. So you can assume X is a smooth, X is smooth complex manifold, you can assume, right? If you don't like the terminal singularity. Then the second condition is Kx, the canonical bundle, being numerically trivial over the base, meaning that if you have a curve containing a single fiber and then take an intersection product of that curve with a canonical bundle Kx, that's going to be trivial for every curve completely containing the single fiber. Okay, that's a setup. So that's a minimal abelian fibration. All right. So here's the big fact that I'm going to use. I honestly don't know the proof of it, but I just use it because people said it's true. Why not? So if you start with a arbitrary smooth projective family of abelian varieties, then the minimal model of this guy does exist. So you can run the MMP here in this specific situation, and then you can always guarantee the existence of it. The uniqueness fails, but there's at least one minimal model which is also Q factorial. Okay, I'm going to use this big fact. Also, I'm going to use this generalization of the fact that I stated before, Néron's construction of the Néron model. So let's say now you have a smooth projective family of higher dimensional abelian varieties, not necessarily elliptic curves, again with a section so that it becomes an abelian scheme over the punctured disk. Okay, then in this situation, your stupid push forward is representable by a smooth and quasi-projective commutative group scheme P over S. Okay, which is a hardcore result. Yeah, so this is a representability result, so you need to actually construct this scheme to show this is true. Anyway, so we're going to use this too. This is the Néron result. Okay, so the Néron model exists and the minimum model exists. So many of our previous discussion almost generalized to this situation for free. So if you start with a minimal abelian fibration with a section, then you can just simply take out the singular fiber, central fiber, to consider it as an abelian scheme because we're assuming there's a section, there's no torsor issue. And then applying the theorem of Néron, you can construct the Néron model formally. Okay, so given a minimal abelian fibration with a section, there's a way of constructing a Néron model. Conversely, if you have a Néron model, then again, you're restricted. So that's an abelian scheme. and then run the minimal model program to get a minimum abelian vibration, although it is not unique. Okay, but the uniqueness will be, so under an additional assumption that we're going to impose soon, the uniqueness will be guaranteed too. Anyway. Okay, so again, the advantage of using this perspective, so basically there's a one-to-one correspondence between the minimal abelian vibration and neuron models. That's what I wanted to say. And then the lower part, you can do the group theory here. You can do addition and subtractions and so on here, which is very good. And the upper part, we're going to do the geometry here. Take the intersection product, take a line bundle, and so on and so on. Okay, so here's the theorem that was partly proved by Néron himself a long time ago, and then Collar. I think part of this was conjecture. I think this part was a conjecture. This part was a conjecture proved by Collar last year, and then there's a little bit of more input by me, but that's just a little bit. So you can just basically think of this as Néron and Collar's result. So the setup is that you start with an abelian scheme over the punctured disk, so you're over here, and then you form the minimal model and the Néron model following this diagram. Okay, so you have this f x to s and p over s, like you have everything. Okay, and then we're going to make this smooth over c secretly. Then you do have this equality that we stated before for elliptic curve vibrations. This still holds for the abelian vibrations. That's true. This is proved by Néron. And the second one is I believe, proved by Collar last year. So this guy automatically extends. There's a unique way of extending this guy to this guy, because P is a Zariski open subset of X. Okay, this is not a trivial result. Okay. So everything behaves super well, even the setup, higher dimensional abelian vibrations. So, but of course, what's missing is a Kodaira's result. So we don't know the classification of XS yet. Of course, we don't know the classification of PS2 because that's a really hard problem. But at least because PS is an algebraic group, right? I told you that the advantage of this guy is do the group theory here so that you can apply the just formal algebraic group theory here. So given an algebraic group PS, you can decompose, quote unquote, decompose it into 3 pieces. The first one is the group of connected components. The second one is this linear part. And the third one is this abelian variety part. So yeah, this part, decomposing into this part is called the Chevalley decomposition theorem. But anyway, so there's this formal, purely formal algebraic group theory that we're going to use. I'm going to write down the dimension of this linear part by delta. All right, so that's my definition of delta. And equivalently, because the linear part and the abelian variety part together forms the connected component of the algebraic group PS, which has the dimension n. There was our assumption relative dimension was n, so equivalently you can assume the dimension of AS is n minus delta. And then the intuition is that the smaller this delta value is, the milder this degeneration of abelian variety is. Okay, so smaller delta means that the generation is mild in some sense, and then you can actually see in the geometry of the central fiber that there is some sort of an abelian variety of dimension n minus delta playing a role. I don't know. Yeah. This is the best I can say, but there's a precise statement of this. But if you draw a specific example, let's say of a minimal generation, and then let's say the delta is equal to 3, so that the abelian variety parts dimension n minus 3, then the central fiber will have a preferred direction of n minus 3 dimensional abelian varieties. Okay, so I told you if delta is small, then the generation is quote unquote mild. So what happens if the delta is as small as possible when delta is equal to 0? So when you have a minimum abelian vibration with a section, and then if you assume delta is equal to 0, then you can say this is a smooth projective morphism of abelian varieties, i.e. this is an abelian scheme. So F is literally an abelian scheme in this situation, which means that there's no degeneration. Okay, that's a delta equals 0 case, which requires a little bit of work, but yeah, it's not too bad. So yeah, that can be done within like a couple of lines. But here's the main result. First main result is top, which is the non-multiple central fiber classification of the non-multiple central fiber. So suppose that we have a minimal abelian vibration of relative dimension n and arbitrary polarization together with a section. Okay, I'm gonna consider the next easiest case, delta is equal to 1. So when delta is greater than 1, I really have no idea, but today's talk will be focusing on the case delta equals 1. And if delta is equal to 1, and then secretly, the total space of X, you can prove this is smooth. That's the reason why I told you, yeah, you can ignore the terminal singularity assumption. Anyway, so in this situation, we have the classification of both the central fiber of the narrow model and the central fiber of the minimum abelian fibration. So what are these? So the first case is a semi-stable case, and it looks exactly the same as the minimum of the fibration. So XS is either isomorphic to 1, 0 is over here, the abelian variety, okay, which I didn't write because that's a delta equals 0 case. So 1, 1 is a P1 bundle with a section 0 and infinity identified. Okay, so there's a picture of this 1, 1 type. What this picture is saying is that I have a P1 bundle over an abelian variety of dimension n-1, and the fibers are all P1. This is not necessarily a product, it can be a non-trivial P1 bundle, but anyway. But it does come with two specific sections, 0 section and the infinite section. There's always two sections. I'm going to identify these two. Okay, so that it becomes like this picture. But the identification may be twisted in a sense that if I identify like this, okay, then what's going to happen is that if I draw a rational curve here, then the rational curve, this guy, will, okay, I erased it. It will not come back to the original. Yeah, so it's going to look like this. So that's the meaning of this, this two different translation. Okay, so this is in some sense a twisted, I don't know, gluing. That's possible. So the Warner type is exactly the same. And the twisting phenomenon also is there, except that you have R number of isomorphic. These are all isomorphic to each other. Isomorphic copies of P1 bundles with two sections, and then it looks exactly like that. 1, 3, for example. Okay. So this turns out to be a consequence of this in the situation, but in the unstable case, this is not. Anyway, so this 1' and 1 are always like coming together, the minimal model and the narrow model. So what happens to the central fiber of the narrow model? This turns out to be isomorphic to ZR times a G extension of AS, which may or may not be trivial. And you can see this because the original P1 bundle may not be trivial. So
sorry, I got lost in the notation a bit. So what was AS again?
I'm sorry. Yeah, AS was, sorry about that. So AS was the abelian variety part of this PS. So remember this.
So it's like linear and abelian and
Yes. So this is an n-1 dimensional abelian, right? I'm sorry. Because the dimension is n-1 because it's n minus delta, and I'm assuming delta is equal to 1. Yeah. So PS is a group object. It's a narrow model. So its central fiber is a Lie group or an algebraic group. So it has a linear part and the abelian variety part, and I'm assuming the linear part is dimension 1, abelian variety part is dimension n-1. That's going to be my AS. Yep. All right. Thanks for the question. Yeah, so PS is isomorphic of this guy, and then you can kind of see in the picture, so you can more clearly see this in this situation 1, 3 fiber, because what's a singular locus of this singular fiber? You can see that the singular locus is a union of 3 disjoint abelian varieties, right? Because those are where the nodes are. So if you pull them out, if you take a complement of it, you can see that it becomes a disjoint union of all these 3 sheets. These are all disjoint union, so that's where the Z3 is coming from. And then GM extension of AS is, this direction is the AS direction, and this direction was the P1 direction, but you pulled out the infinity and 0. So that's going to be a GM fiber bundle over AS, which is a group. Okay, that's what's happening. All right, question about the semi-stable fibers.
Yeah, so in case 1, for the P1 bundles, so are these really projectivizations of rank 2 vector bundles on the
Yes, it is. Yes,
okay.
it's
How do you describe those? Can you describe those bundles explicitly, or how do?
Oh, I'm sorry. It is not just the yes. So yes, you can. So it is of the form. Sorry, it's I want to write it down here. So it is a projectivization of a line bundle plus O. Yeah, it's this type of
Okay, yep.
yeah, does that make sense? Okay.
Yep.
And this line bundle, why do we have this line bundle? Because this is basically this GM torsor. Yeah, this GM torsor is that line bundle, and it's compactification. Yeah, thank you for the question. Are there any more questions? Yeah. Okay, so that's a semi-stable fiber, which was pretty satisfying, I believe. I don't know. At least to me. So the unstable case is actually a little more surprising in some sense because it's going to be basically a product on the nose. So what that means is that XS is isomorphic to a product of a curve by this abelian variety dimension m minus of dimension n minus 1 divided by a group action G, okay? Where C is the unstable curve classified by Kodaira. It's, Kodaira type 2, 3, 4, 1R star, 2 star, 3 star, 4 star, this possibly non-reduced and highly reducible curve. Anyway, so that's this curve C, classified by Kodaira, and then you literally take the product with AS. And then what is this group G? G is a finite abelian group. It's actually a subgroup of 0, Z2, Z3, Z4, Z2 squared, which appeared before. That's the component of the neuron group before for the elliptic vibration, but also there's an alternative description that it turns out this is precisely the discriminant group of the Cartan matrix of affine AD Lincoln diagram. So it turns out this discriminant group is either one of these 5, and then G has to be a subgroup of it. Okay. And then finally, this G acts on this guy diagonally. So the second factor is literally just a translation, and G acts on the first factor by a quote translation. It's because this G action, there's a preferred way because this is the way how G acts on the elliptic vibration. Because I told you G is a subgroup of the narrow component group. In the narrow component group, there's a preferred way of narrow component group acting on a central fiber and the minimal elliptic vibration using I described as a translation. Anyway, so there's a unique preferred way, that action. So that completely describes this excess, which can or may not be reduced or non-reduced. So what about the narrow model, the central fiber of the narrow model? The narrow model is isomorphic to this discriminant group, which is either one of the 5, divided by G, because G was a subgroup of that. So it's quotient by GA cross AS. So there's no extension. This is literally a product. Yeah, so let's draw the picture. So when C is a Kodaira type 2 curve, which was, remember that this is a cuspidal rational curve. So there's this cuspidal rational curve, and then I take a product with this AS. This is the AS direction. AS, and this is the cuspidal curve. Cuspidal rational curve. I literally define a product, and then in this situation, what can be the possibility of this G? G turns out to be a discriminant group of I think it's either affine. Yeah, I'm not sure if affine A0. Okay, so anyway, G has to be G is a subgroup of the trivial group. So G is always necessarily trivial in this case when C is a type 2 curve. So there's no other possibility. It has to be the product. Okay, that's a central fiber. So what happens when you have C equals the Kodaira type 10 star? A Kodaira type 10 star curve there's a multiplicity to this part, and then there are 4 multiplicity 1 rational curves attached. Okay, so this circle part is the AS, and then this, I just took the product. So that's a possible central fiber that can arise according to our classification. But then in the situation, your G turns out to be a subgroup of Z2 squared, which is the narrow component group of the 10 star fiber. So if I take the quotient by Z2 squared, the entire Z2 squared, so this is, I made up my type, made up the name of the type. So this is C cross AS divided by G, where this 10 star indicates that C is a 10 star type, and 4 indicates that G has order 4. Anyway, so I just completely made it up, but that's how I use. So this is this, and then you can see that there's a preferred way of the group action, which I didn't describe, but it's basically acting a translation by torsion points on AS, so you have to shrink the circle by 4, although it doesn't look like 4. And then what happens to all the 4 reducible components? It turns out this G action is, swapping all these cycling all these curves, so you identify those. So what's basically happening is that if I have a point here, then this point, according to the action G, is sent to here. And then since G is Z2 square, there's another part which is sent to the other one, and this is over here. And then if you all identify them all, take a quotient, it's going to be connected to a single spring. So we'll call it a spiral staircase. That's a possible singular fiber that can arise with a central pillar with multiplicity 2. So this is similarly, you can play the same game. This is the 1 star, 1 3 star divided by 4. So 1 3 star fiber is here. This is the Kodaira 1 3 star fiber. Okay, and then you take a product with an abelian variety dimension n-1, and then take a quotient by Z4. And then it turns out the picture is like this. Yeah. The Z4 quotient can sort of mess up the picture, but yeah. This is what's happening. All right. Okay. Question about the unstable fiber situation. Right. So the core, somehow surprising, at least to me, of the unstable fiber situation is that this narrow component group. Well, okay, so this guy always splits because it's a finite group, but the neutral component of the narrow central fiber, that by definition, because it's unstable, this has to be GA extension of an AS. Okay, so the Chevrolet exact sequence of
Great. Can I just interrupt to ask a question?
Sure.
Yeah.
Please.
So in the higher dimensional case that you're doing, so do you get more than in the classical case for an elliptic? Are there more possibilities? Which ones are those?
That's right. Yeah. These two ones are more possibilities in some sense because this is a Kodaira, like classical elliptic curve Kodaira central fiber.
Okay.
This one is an abelian variety dimension n-1, which is nothing special, but there's an additional quotient, possible quotient. So the possible quotient gives you additional, finally, many more possibilities.
Okay. Thanks.
And the quotient is, by the way, the quotient is a free quotient. This action is a free action. Yep.
Okay.
Yeah, thank you for the question. Further questions? Okay, so again, at least to me, what's surprising? Yeah.
Sorry. So, do you have the each explicit example of which realize these possibilities? So
yes, all the classification results I'm gonna state, even including the multifiber, are realizable. Yes.
So every possibility can be realized.
Yes.
Okay.
There are examples. Yes. Yeah. So actually, So in this situation, it's actually not very. It's kind of stupid. I can tell you in like 30 seconds. So if you take a minimal elliptic vibration, this is literally a minimal elliptic vibration, relative dimension 1, and then take an abelian variety dimension n-1. So I take an abelian variety dimension n-1a. So that turns out to be a minimal abelian vibration of dimension n, which does have the delta equals 1 value. So what is the central fiber of this guy? The central fiber of this guy is XS cross A. So this guy is realized. But how do you realize this G quotient? I take a global G quotient of this. There's a way of taking the global G quotient, and then I can realize this G quotient central fiber. That's it. Yeah. So all the possibilities can be realized easily. Okay, so the unstable, by definition, the unstable situation, fiber situation, is where the neutral component, the neuron component, central neuron fiber, sits in this Chevrolet exact sequence. But then what I'm claiming is that once the sequence exists, then it necessarily splits. So in other words, in other words, if you have an algebraic group, which is a non-trivial GA extension of AS, that doesn't have a smoothing, that doesn't have a generation to an abelian variety at dimension n. That's what yes, which was quite surprising to me, and honestly, I did not believe this for a long time, but I don't know. I think I do have a proof for that. Yeah, I do have a proof. It was written in the file. So if you are skeptical about it, you can please check and then yeah. So that was morally so perhaps this moral reason may convince you a little bit. So in this situation, if you compute the X group of AS comma GA, it turns out this is the same as there's an isomorphism OAS. So that's C to the N, which is a torsion-free group. As an abstract abelian group, it's a torsion-free group. But there's a projectivity assumption lurking behind. Everything was projective. And then my impression was that if you have a projective thing and torsor under a projective thing, everything somehow should be torsion. Like the extension class should be torsion. So what's a torsion class in the CN is just 0. So it's necessary. But that's how I sort of like try to justify it. Yeah. Of course, proving it's a torsion that's a proof of this. Okay, so that's the end of the non-multiple fiber case. So this is the multiple fiber case. So let me be a little let me cover it a little quickly. So the main idea, actually this is not a main idea, but the starting point, which is very well known, by the way. This is not my idea. So let's say you have a minimal elliptic fibration where the GCD of all the coefficients of the irreducible component is by definition M, and that's greater than 1. That's my definition of the multiple fiber. Okay, so in this situation, there cannot be any section whatsoever because the central fiber does not have any reduced component. So, but what you can do is that I can basically take another complex unit disk and then take this, ramified covering, and then I take a base change and then take a normalization, which is basically the same as the semi-stable reduction, business. Then this will be another minimal abelian fibration. Okay, and so in particular, this Y is terminal or even smooth in our situation. Okay, and then this does come with a section because we basically clear up the multiplicity by taking the normalization. The normalization is to clear up the multiplicity. So we can apply all our previous classification results to this guy, and then try to depict the central fiber of this guy by the quotient of the central fiber of that guy. That's the strategy, which is again well known. But the classification of what kind of quotient is possible, what kind of action is possible, is I don't know. It was a headache for me. Well, anyway, so you can apply. That's the first strategy. So because this is a minimal abelian fibration with a section, you can form the narrow model and so on and so on. Of course, you can form the narrow model here if you consider the torsor ratio, but there's another narrow model, Q over T. So there are two narrow models now. So here I have a narrow model P using this, taking care of this torsor business. I can always form the narrow model. And then over here, I have another narrow model Q, which is a Zariski open subset of Y. So P is not a Zariski open subset of X, but Q is. The two narrow models over two different bases. Okay, so this is the multiple fiber version of the classification. So let's say in the previous situation, multiplicity M greater than 1, so there's no section at all, and then assume that delta equals 1 as usual. This is our setup. Then if you clear up the multiplicity, simply divide every coefficient by n so that there's at least one coefficient, so the reduced component. By the way, this is not trivial, but there's a lemma that there's a lemma saying that there's a reduced component of this. In other words, if M GCD AI is equal to 1, then this implies there exists an AI equals 1. There's something to check, but this is true. Okay, so what do I? So so I'm gonna divide the case by 3 by taking care of the previous diagram. Unfortunately, I don't have the previous diagram. So let me draw the previous diagram over here. Okay, this is the original multiple abelian fibration X over S, and then I took a ramified base change of 3M. And then this is a new minimal abelian fibration with delta equals 1, 2. Delta is preserved. Delta actually can decrease, but let's not think about that. So if this guy, so there are the two narrow models, P over S and Q over T. So it turns out when P is semi-stable, then that forces Q to be semi-stable. So the semi-stability can never go bad under the base change if you have a narrow model. So P semi-stable implies QT is semi-stable. Anyway, so that's the assumption. Then your central fiber, the original guy, divided by M, this guy, is again a cycle of P1 bundles, as in the type 1R, but there's a little bit of subtlety. The subtlety is that what was the description of the 1R fiber? It's a cycle of P1 bundles, but in the previous situation, all the P1 bundles are isomorph to each other because those are compactification of the GM torsor, the same GM torsor. But here the EIs may be non-isomorphic. Yeah, that's a little bit of subtlety, but basically that's the only difference. Yeah, so it looks similar. Behaves as if it is a semi-stable fiber. So it's a semi-stable like. So this second situation is a mixed situation between the semi-stable behavior and the unstable behaviors. So this is the case when the first neural model over this S is unstable, but the second neural model over T is semi-stable. Okay, that's possible because you improve the semi-stability. Unstable to semi-stable, that's possible. You can never, make it worse. So in this situation, it's a quotient of a 1R type, semi-stable fiber by an involution. And this involution is a free involution reversing the orientation. So what does that mean? So for example, let's think about the 1,6 fiber. Then my involution, Z2 involution, can swap these two, 1 and 6, swap these two, 2 and 5, swap these two, 3 and 4. Okay? So if you swap the two and 5 to two components 2 and 5, then those are identified. Okay, so this becomes a single 2 and 5. Those are isomorphic. This is how I drew it. This is isomorph to this guy is isomorph to this guy. But what happens to the case when you identify 1 and 6? There's an intersection. So over the intersection, you're not acting it trivially, but acting it by translation in order to element in the abelian Braddock dimension n-1. So the overall quotient will be a singular guy looking like this. Okay, this is actually, singular. This irreducible component is singular along this guy. So this is not a P1 bundle. Anyway, so this guy is the same thing. So you have a similar shape like this, but a little different looking. Yeah, so that's possible. That's the situation 1. The situation 2 is that my involution preserves 1, identical swaps 2 and 6, swaps 3 and 5, and preserves 4. So in this situation, this 1 becomes a quotient of the single component, which is still a P1 bundle over abelian variety divided by 2. But if you identify 2 and 6, it's going to be this guy. 3 and 5, this guy. Again, 4 is. So that's what can happen. So geometrically, they look different. So that's case number 2. I call this 1,6 minus and 1,6 plus. Finally, both the narrow model can be unstable, and then as you can expect, it can be the central fiber XS divided by M can be unstable fiber, classify anything on this one classify above. But a little bit of surprise is that there are exceptional cases. And actually, this exceptional cases were already observed by Matsushita in the case of Lagrangian fiber hyperkähler fourfold. But this result is, in some sense, generalizing his result. So what can happen is that there are 6 exceptional cases. I wrote them all. So the first exceptional case, I wrote them as 1, 0 star A because it looks like 1, 0 star. And then I drew it wrong. So it has to be, this guy, these 2 rings are not interchanged. Yeah, so only 2 rings are interchanged, the bottom 2 rings are not interchanged. Okay, that's how it looks like. And then, so confusingly, these 2 are looking the same. If I draw it like this, they're looking the same, but they're not isomorphic. And then this is looking exactly the same way to the 1, 0 divided by 4 that I drew before. So 3 are somehow looking similarly, but they're not isomorphic. And then there's yet another guy where you cycle these 3 rings, and then the 1 ring is not cycled, it's preserved. And then this is 4A, where you swap the 2, and then this one is preserved, and then 4 star A. Okay, so that's actually it. didn't prepare any kind of proof strategy whatsoever because I don't know, the version that I have is a little too long, but I'm happy to answer any kind of questions about the proof because it's still fresh in mind. Yeah. Thank you very much. All right. Are there any questions?
Sorry. Hi. Hi.
Hello. Yeah.
Yeah. In your next
Hello?
page, in the next page.
Oh, yeah, here. Yep.
So the first graph.
Yes.
So there's a case that two rings are in a cycle and another two are separated.
Yes, that's right.
Also, they are different. This case is different from
Yes,
the
this
one
case
you.
never, yes, that's right. This case sort of breaks the symmetry in some sense. So this never arose in the usual unstable fiber because the unstable fiber was of the form C cross AS divided by G, where G is acting completely symmetrically. So this can never happen. This kind of picture can never happen. If you swap these two, then it should have swapped these two too. But in the multiple fiber case, the symmetry can be broken.
Can you say a little bit more about the construction of neuron models? So Kohler's construction of neuron models using MMP. Does this apply to the particular case of abelian fibrations, or is it more general, or how should we?
This is, to my knowledge, that's only for abelian fibrations. Yeah.
Okay,
So-
and then I guess so. In your proof, it seems so the group structure on the central fiber. I mean, that's sort of the key thing you're sort of.
Yes, it plays a key role, but that's not the only. Yeah, so you gotta like go back and forth from the minimum model and the group structure, and then utilize them both. Yeah, it becomes they have pros and cons.
Okay, very interesting. Thanks.
So, I think in this term you assume the delta equal one case, and
That's right.
I saw your paper just you put on archive. So
Yes.
you write the delta regular one. So
Right.
so but
yes, right.
this means in this case S is a curve, so delta regular implies that delta equal one.
That's
So
right. That's right. That's exactly what I'm. Yeah.
so it does not mean that this theorem cannot apply the delta equal 2.
No, right. Mhm.
I mean the codimension 2 singular fiber
Mhm.
case. We cannot apply this theorem.
Right. So this theorem only applies to, so if given so I didn't explain the word delta regular. So the delta regularity is by definition, if you have a higher dimensional base, not necessarily a curve, let's say the base is smooth, then you can consider, let's say you have some neuron model or some smooth group scheme or something like that, and then the delta regularity means that over the codimension 1 points on the base, the delta value, the linear part of the group scheme is 1, codimension 2, linear part is 2, codimension 3. So if the deeper you go, the linear part grows. Yeah, that's the delta related assumption for higher dimensional bases. So when you assume that base has dimension 1, and this condition is exactly saying that this delta is at most 1 because it's codimension 1. So it's either 0 or 1. But if you have the delta regular abelian vibration, and then you go into codimension 2 points, then delta goes to 2. So definitely this theorem does not apply. So you can try to generalize, although I didn't explain any proof strategy whatsoever, you can try to generalize this kind of thing to the case delta equals 2. I believe, I don't know, I really have no idea because my proof really depends heavily on the delta equals 1 situation, but I got the impression, so you can either do the following too. So you can either consider a degeneration of an abelian variety to delta equals 2 case directly. So it's a degeneration of a one-dimensional abelian variety. Or you can consider the degeneration of a two-dimensional abelian variety and then preserve the delta regularity. I think the second setup may have a little better hope because I got the impression that the delta regularity should be really important. So yeah, I'm not answering your question at all, but like my impression is that if you want to understand the delta equals 2 fiber, then maybe considering only a one-dimensional generation is not a good idea. Maybe considering a two-dimensional generation is a better setup. I don't know. That's the impression that I got. Yeah, but I really have no idea.
I see.
So maybe just sort of to clarify in the previous question. So okay, but didn't we discuss before that somehow if the family is not over curve, then we don't have this minimal models and neuron models? So did I?
Oh yeah, so the existence of the minimal model and the narrow model doesn't depend on the delta value. It's a purely abstract hardcore theorems, which is done by many amazing people. So this doesn't use any delta value at all.
No, but does it use the dimension of the base? So
Oh, it uses, wait, does it use it? I don't think so. I think the existence of the minimal model is for arbitrary dimensional base. Maybe like, let's say the base is regular for obscurity. Narrow model, as I said, for higher dimensional cases, narrow models frequently fails to exist. But if you're interested in symplectic varieties and Lagrangian fibrations, they do exist because of my previous result and also in preparation with Mark DiPotato and Christian Snell. Anyway, yeah.
and
Sometimes
for
it exists.
delta equals 0, you don't know what you mentioned that for delta equals 0, it's you don't
Oh,
know.
when delta is equal to 0, when the central fiber has delta equals 0, it should be, yeah, it should be an abelian variety.
Yes.
And the original vibration is just, you know, family of abelian varieties with projected family.
Okay, if there are no other questions, let's thank the speaker again.
Thank you for the invitation again.
Thank you very much for the nice talk.
Right.
I will so I'll close the meeting now. Okay, thanks
Okay.
again for
All right. Have a good day.
okay. Have a good night, I guess.
Yeah, right.
Bye.
Thank you.